Okay, well, hi everyone. I know we have participants registered from all over the world, so it'll be good morning, good afternoon, or good evening, depending on where you are situated. And welcome to our webinar on consequences of reduced sea ice cover in the future Arctic Ocean. And thank you very much for taking the time to join us here. I know you're all busy, and I'm very happy to see so many people join the webinar. My name is Marianne Tronstad Lund. I'm a senior researcher at the Center for International Climate Research in Oslo, Norway, and I'll be taking you through this 1-hour event. And I just also have to note that this webinar is being recorded. So I don't really need to spend time motivating the context of the webinar to anyone in this group. I assume we are all very much aware of the rapid changes that are ongoing and have been happening in the Arctic and the polar regions for a long time now. This figure now concludes the 2024 annual September minimum sea ice extent, and it is now observed that the rate of change of Arctic summer sea ice is shrinking by 12% per decade, with a lot of intraannual variability, of course, but overall dramatic changes. And these dramatic changes are also evident from other variables such as sea ice volume, sea ice age, and they are very clear on a number of elements of the cryosphere. We also all know that sea ice and the cryosphere in general are essential components of the Earth system. And so the rapid changes in sea ice and climate and environment in the polar regions are having wide-reaching consequences, both within the polar region themselves, but also consequences extending far beyond the borders of the polar region. And these involve interactions across the ocean, ice, atmosphere system. And to be able to understand and reliably project the consequences, we do need to be able to understand and formulate the underlying processes within each of the compartments of this ocean ice atmosphere system and how these function together and into combined form interactions with the entire Earth system. And this is what's the focus of the EU project CRiceS, Climate Relevant Interactions and Feedbacks, the key role of ice snow in the polar regions and the global climate system, which are the organizers of the webinar today. And this project is funded by the European Union Horizon 2020 Research and Innovation Programme, and it focuses on improving model predictions of the role of polar processes in the climate system, focusing on the detailed processes that are ongoing within heat, mass, and momentum exchange, aerosols and clouds, and biogeochemical cycles and greenhouse gas exchanges within the Arctic region. So the project concept centers a lot around linking knowledge of detailed processes, starting from observations, using observations to improve parameterizations and descriptions of the processes for process models, regional models, and then bridging these into the coupled climate system and then seeing how we can improve and deliver updated climate projections that can be used for polar and global risk identification and impact assessment. And now entering its final year, there's a lot of activity that has happened and a lot of activity that is ongoing. And this is what we want to give you some tastes of at today's webinar. So this webinar presents new research on future Arctic Ocean and consequences for that. We have a lot to go through in an hour. So we'll be starting with two 15-minute presentations by Morven Muilwijk from the Norwegian Polar Institute on the Arctic Ocean, the title Arctic Ocean Unrecognizable in 100 Years, and then followed by a talk by Julienne Stroeve from UCL London Global University on future Arctic sea ice and implications for Hudson Bay polar bears. After that, we will have a panel discussion where Morven and Julienne will be joined by Letizia Tedesco and Stefan Fronzek, both from the Finnish Environmental Institute. So I will also monitor the chats. We do have quite a tight schedule, but if there is time, I will pick up questions from the chat in the panel discussion. So please feel free to write your questions there. And if there isn't time, then hopefully our researchers will be able to pick up on them and answer you individually. So I think without much more delay there, I will give the word to Morven, and I will stop sharing my slides. Morven, please, the floor is yours.
Yes. Thank you very much. Do you see my screen?
No, we don't see your screen.
No.
I see the screen.
Perfect.
Okay.
Yes, people see the screen.
I
Very
see
good.
you.
I see the screen.
All good. Thank you very much for this very nice introduction. My name is Morven Muilwijk. I'm a researcher in physical oceanography and climate at the Norwegian Polar Institute. And today I want to start with bringing you along to the Arctic Ocean. So last summer and also in 2022, me and my colleagues, we were on a cruise with our research icebreaker, Kronprins Haakon, as far north as you can possibly go, to the North Pole and the surrounding areas. It took us about 5 days from Svalbard to reach the pole, which is a very sad record. And this was, of course, mainly due to the thin, rotten ice and reduced sea ice cover. And the picture that you see on the screen here is maybe not what you expect from the central Arctic and the North Pole area. More open water than ice and much more blue than white. But this is perhaps becoming more and more common. It wasn't surprising, though, of course. The Arctic, as mentioned, is changing fast, and 2024 was the second warmest year on record. And as we've witnessed, Arctic sea ice is getting thinner and thinner by the year. We also know that there's more and more leads, open water areas, and according to satellite data, less and less ice survives the following summer. So we're left with very little thick multi-year ice. And this is, as mentioned, a scary indicator of a substantial shift in the Arctic climate system. Now, the Arctic is already very different from the Arctic that was studied by my supervisors and people before me, but even from when I did my first Arctic research cruise in 2015. And I think last year, when we were looking out from the portholes of our cabins on the ship, I think there was this one question we all had. How is this going to continue, and what will the Arctic Ocean look like? For example, in year 2100 or in the more nearby future. And this is something we've also been working with at the Norwegian Polar Institute and in CRiceS using climate models. So what can models tell us about the future Arctic? Although there is still quite a bit of uncertainty and spread in model projections, I think all models agree that the recent observed trends are expected to continue. Most recent estimates suggest that we can expect a nearly ice-free summer in the Arctic sometime between 2040 and 2060. Although there is quite some uncertainty as seen from this graph where we show various CMIP6 projections under a high greenhouse gas scenario. But one thing we also know is that the ice is getting thinner, and the graph on the right here shows from CMIP6 model simulations that the winter sea ice thickness is also gradually declining to less than a meter on average. More open water and thinner ice has a lot of implications, what we're talking about today. And it'd be difficult to mention all of those, but one of the main effects in the Arctic is that sea ice acts as a lid on top of the ocean. So it shields the Arctic Ocean from the atmosphere. One of the things it does is it makes sure that not all solar light penetrate. But what I've been focusing on, that it also limits the and mediates the direct effect of wind on the ocean. Wind is an important contributor of kinetic energy to the ocean in general. It creates waves, drives surface currents, and stirs the upper layers of the ocean. In the Arctic, this momentum transfer from the atmosphere to the ocean is mediated by the ice pack, and is hence a combination of open water and under ice surface stress. Now, in today's Arctic, a lot of the wind energy is absorbed by internal stresses in the ice pack and also lost due to ice dynamics and ice deformation. So obviously, with less ice, less kinetic energy is being absorbed by the sea ice pack, and wind can more directly be transferred to the ocean underneath, which is one of the critical impacts we've been studying in CRiceS. However, it's not only the ice that is changing, also the atmosphere is changing a lot in the future Arctic. We know it's warming, but due to this warming, the large-scale dynamics are also changing. And climate models, they show that as the climate continues to warm, we can expect average wind speeds in the Arctic to increase. And as we show on the figure on the left here, the multi-model mean from CMIP6 shows around 2% increase every decade in winter and fall wind speeds. So we're not only getting a more direct transfer of energy to the ocean, we're also increasing the winds. And the combined effect of these two changes is a large increase of momentum transfer, as we can see on the figure on the right here. And from these graphs, the multi-model mean shows that the increase in momentum transfer is approximately 5% per decade. And these changes are particularly large during winter here. There is a big seasonality in both winds and in the momentum transfer to the ocean. It is already relatively low during summer because this is when we have weak winds, but also the changes are largest during fall and winter season. This seasonal discrepancy is very interesting and something we spent a lot of time investigating in detail. Whereas these figures here summarize some of our findings using the model simulations, starting on with the stress, so the average surface stress that the ocean feels on the figure on the left per month. So the x-axis here is the months of the year, and we're showing both the recent years, which is the blue graph here on the left, and the orange showing the end of the century projections from CMIP6 models. We see on average the surface stress on the Arctic is very low during summer months, with its minimum in month 7, July, and relatively high in fall and winter. And as we see, the orange line increases this in most months, but not during summer. And this is because it mimics the pattern of the wind, which is the next paddle right next to it, which looks very similar with low surface stress during summer, highest during fall, and this is also when the increases are larger. However, there's not a direct match between wind and surface stress, and this is because the ice is also changing and impacting this seasonality. And this is where we see biggest changes in winter. During summer, the ice concentrations are generally already very low in the Arctic, but it's during winter where we're really shifting from a pretty much fully ice-covered Arctic Ocean to a somewhat lower sea ice coverage concentration. This results in a much more dynamic and loose ice cover, which then impacts the internal stresses in the ice. So when the ice cover is much more loose, the internal stresses in the ice are much less, and this is what we see from the figure on the right. Generally, this was very high stress in the Arctic sea ice during winter, meaning that there's a lot of tension and it's a very rigid ice pack. And as the ice concentration decreases, it becomes more loose, and there's much more of a direct transfer of energy from the atmosphere to the ocean underneath. And this effect of a weakening ice cover is primarily important during the winter months when the stresses were high to begin with, and they don't really change at all during summer and fall because they were already very low to begin with, as we can see from the figure. So This mechanism that we explain with how the internal stresses impact the transfer of wind energy is very important during winter and amplifies this increased wind speed strength, and makes the result of this is that the impact on the ocean is largest during winter when it comes to momentum transfer. So now the big question is, of course, what is the impact of this, and is it important at all? There's a lot of changes going on. This is just one of the things. And back on the ship in the Arctic this summer and previous years, we've been measuring ocean currents and particularly mixing under the ice. You can see a photo of us lowering an instrument in this year's cruise. And we do this because mixing is very important in the Arctic, especially because it contributes to bringing nutrients upward in the water column, where there's then light available and they can be used by phytoplankton to grow. It's also very important because mixing can contribute to bringing oceanic heat upwards towards the surface. And here this heat can then again contribute to melting the ice from below, further amplifying the decrease in ice extent. Now, in general, the Arctic is very calm with weak currents and very little mixing. However, in our recent study, we do show that as the wind becomes stronger, the ice disappears and weakens, the ocean currents will strengthen. And towards the end of the century, we can expect that the surface currents in the Arctic, on average, are expected to be approximately 30% stronger, which is quite a big increase. Although we must note that a 30% increase of little is still quite little. We also showed that in the models this results in more turbulent mixing in the uppermost layers. However, it is also important to note that these changes are largest during fall and winter, but that there's no very clear trends in the models during summer. And this is actually when maybe the nutrient mixing is most important. It's also important to remember that there's many other changes occurring in the Arctic Ocean, such as changing freshwater content and stratification, which again might limit how deep, for example, this wind energy can penetrate and how large the effect of this additional energy input at the surface is. Now, these climate models are far from perfect, and many of the processes we investigated are simplified and poorly represented. And we know that many of the ocean properties are heavily biased in CMIP models. However, we are fairly confident that we are slowly transitioning from a very calm and quiet Arctic Ocean to a slightly more dynamic ocean with more open water, stronger winds, which then results in an increased momentum transfer, which then can drive accelerated currents and more mixing. And this may have large impacts on, for example, the Arctic ecosystems. So there's still some uncertainty, and I don't have all the answers, but I do know that the future Arctic Ocean will be very different from the one that we know today. And I'll stop there until we'll discuss this further later on.
Thank you very much, Morven. Excellent presentation and excellent timekeeping. So for those who came in a little late, just to remind you that you can put your questions that you might have to any of our two speakers in the chat, and we'll try to return to them during the panel discussion if there is time for that. All right, so moving on. Julienne, you're still here? Yes. Excellent. We can't hear you yet. I think you're muted. We see your slide.
Okay, yeah, sorry. Too many buttons to push. Yeah, so thank you very much for having me. And a little bit of what I'm going to say will be somewhat of a repeat of what we've just heard from Morven, although it's going to be a little bit more focused on, how we use the climate models to then do ecological studies, like look at implications on marine species like polar bears. So we already saw this, but I just thought it was always good to kind of recap where we're at with Arctic sea ice. And of course, 2024, it wasn't a new record low or anything, but it was the 6th lowest. And we're certainly in this sort of new Arctic regime where we just have basically a lot less sea ice all around the Central Arctic Ocean. And pretty much most years since, 2007 have been below 5 million square kilometers with a few exceptions. So we're kind of in this new Arctic regime. Interestingly enough, oops, is this working? This December, we set a new record low, which was a little bit surprising, but the reason I'm showing this is because the Hudson Bay area, and especially the southern part of Hudson Bay, did not freeze up already by the end of December, and it's still not completely frozen up as of today. So this was actually explaining about 30 to 40% of the record low that we had in the winter sea ice extent this year for December. We also have low conditions still in the Barents Sea and a little bit also in the Bering Sea, but it really was driven by what's going on in Hudson Bay right now. And I also just thought it was interesting to just update this graphic that Dirk Knotts and I had produced in 2016, where we were looking at, the relationship between sea ice loss and cumulative CO2 emissions and whether or not we still have this linear relationship. And, when you plot it all out, it still falls on this linear line pretty well, although the slope is not as steep as it was when we first did our paper, which was showing at about 3 square meters of sea ice loss per metric ton of CO2. But we know the main driver of sea ice loss still has to do with the warming from greenhouse gas emissions. And so then, of course, we think a lot about, well, what will the future hold then? And I like this graphic because it really kind of highlights to me that any children born today are facing a very different world than the ones that we're experiencing right now. And, if you're looking at different warming scenarios, whether or not a human, when they're 70 years old at the end of a century, will have 4 degrees of global warming, versus today where we're only having maybe 1.5 degrees, it's going to be a very different world. And we were looking at this a little bit more just for the Arctic itself and looking at, what were the warming levels pre-industrial, what is it at 1.5, and what is it at 2.7, because that's the current reality that we're facing. If every country were to commit to reducing the greenhouse gases that they've agreed upon, you're still getting to a warming of 2.7 degrees. And if you do that, and you look at annual temperatures, for example, pretty much almost every day of the year will have temperatures that exceed anything that we saw in pre-industrial if we hit that 2.7 degrees. Even at the 1.5 degrees, we're already experiencing temperatures that are on the extreme end of anything that we had seen in pre-industrial. And of course, that signature is much stronger in the autumn, and we can see temperatures exceeding 10 degrees Celsius in the wintertime, in the autumn in the Arctic Ocean. So we're looking at a very different Arctic as we hit these kinds of warming levels. Now, another way to kind of look at this, and we did this for a paper that's coming out February 7th, it's a Science Review article, and we were just looking at, okay, what does the Arctic Ocean look like? And of course, we can have the pre-industrial level, which is also really what we had throughout the early part of the 20th century, and then what it looks like pretty much today, and what it will look like at 2.7 degrees of global warming. And for sure, if we're hitting those sorts of warming levels, it's not just that we've lost the September sea ice, but we will have lost it for about 4 months out of the calendar year. And even at 1.5 degrees, we cannot rule out that there might be some occasionally ice-free summers already emerging, although typically we had sort of estimated that it would really happen at 1.7 degrees of global warming. But the recent work that was published, I think it was in December, with Alexander Jean, looking at the daily sea ice extent, that even daily sea ice conditions could be dropping below 1 million square kilometers, even before the sort of 2050 mark that we often talk about for September as a whole. So we're looking at a very different Arctic Ocean. And so one of the things that I've been interested in, especially when I'm thinking more about, whether it's impacts on shipping or impacts on biology, is how long of an ice-free period do we expect to see? And actually, Alex Crawford and I, we did this study back in 2021 where we were trying to look at the open water period in the CMIP6 models and trying to see, one, how well do they compare with the observed, and two, of course, how do we use that to look out into the future? So we chose the basic NSIDC regions because we really wanted to do a regional assessment, and looked at, the distribution, which is in white. It's going to be the observation with the observational uncertainty with the X's. The solid red circles is going to be the multi-model mean. And then all the different lines are going to be individual simulations. And if you looked at the Arctic as a whole, you would say, well, the models actually do quite good. They're capturing the mean open water period length over the observational period, and everything's within the spread, so it looks pretty good. But if you start looking at individual regions, then you start seeing that there are some biases. And in particular, many times the observations show a shorter ice-free season length in many of the regions than what the multi-model ensemble mean is showing. And this would then bias your predictions if you wanted to say, well, we're expecting this many months of ice-free conditions. Sometimes it does happen the reverse way too, where the models are underestimating the length of the ice-free season. That's particularly true in the Barents Sea, for example, where there's an underestimation. But you can see that, sometimes it works okay in certain regions, and like Central Arctic Ocean looks okay, but in some of the marginal seas, it's not matching as well. Oh, sorry. Interestingly enough, though, when we look at the trends or we look at the climate sensitivity, so the open water period per degree of global warming, then we start seeing much larger biases emerging. So oftentimes, some of these models may be getting some of the answers right, but maybe not always for the right reason. And especially when we're looking at the sensitivity to warming, all the models mostly are underestimating the sensitivity to the warming that we see within the observations. And when we're looking at the trends, for the large part, a lot of the models are underestimating the trends in the ice-free period. And so this is just another way we can look at this in terms of these periods where we have, or regions where we have underestimation, for example, in the Gulf of St. Lawrence, the Hudson Bay region, which is important for what I'll talk about later, the Beaufort Sea, so there's some regions where it's definitely underestimating the length of the ice-free period. And of course, there's other regions where it's actually overestimating slightly, so like in the Barents Sea. But this is relevant then in how we use these model projections if we wanted to start doing different studies, like if we wanted to look at how shipping will change in the Arctic, or if we want to look at, how will the ice conditions and longer open water periods influence polar bears, which is what I'm getting more and more interested in being in Canada. So I'm going to switch then to come over to Hudson Bay. And we did a test study this year where we looked at sea ice conditions in Hudson Bay and the future model projections, and tried to see if we could constrain a little bit better what we expect to happen to the ice in the region and how it would influence the polar bears in the region. Now, most of you probably know that Hudson Bay is a seasonally ice-covered region, so it's completely ice-covered in the winter, and it melts out entirely in the summer. So the interesting thing, though, is the way that things freeze up and the way that things melt out. As you would expect, it's going to freeze up first in the north, in the northwest, and probably last in the south and the southeastern part. So areas like Fox Basin will start to freeze already in October, and the last area to form ice will be in James Bay. But then the breakup is actually a bit different, and part of that is because the dominant wind patterns are actually transporting ice from the north-northeast, so around Churchill area, across Hudson Bay, down towards James Bay. And so actually that region down south is one of the last regions to melt out, because that's where the thicker ice tends to pile up. And so what's important for the bears in this region, like in James Bay, is that because the ice tends to stay around longer, they have a longer amount of time on ice before it breaks up in June or July to go out and feed and hunt for seals, which is actually quite good for that polar bear population, whereas the polar bears around Churchill will have the ice breaking up earlier compared to the southern part. Excuse me. So this is just some telemetry data, and you can kind of see these individual tracks. These are polar bears, and these are polar bears waiting for the ice to come back. But as soon as it comes back, they are out on the ice. And it's pretty remarkable that I mean, it's just a little bit of ice and they're immediately jumping back out on the ice. They've traveled quite far, I think a little farther than I would have expected them to travel. And then as the ice melts, some of them try to linger on the ice for a little while, but eventually they're forced on shore where they're going to have to fast or try to feed on fish or maybe a caribou if they get lucky until the ice comes back. But as soon as that ice is back, they're back out there. So in our study, we broke out the Hudson Bay into two regions, the Western Hudson Bay and the Southern Hudson Bay, in part because those are the two most well-studied polar bear populations, for which we had some telemetry data for comparisons with the satellite data and also then using that to constrain the future projections. So one of the things we did a little different than what's done in other studies is we also decided that it's not just if ice is there or not, but that the ice has to be good enough for the bears to be able to go out on. And so for us, we decided, well, a 10 centimeter threshold for thickness is probably the best kind of estimate just based on observations. Like this is a polar bear trying really hard not to fall through, which looks to be quite thin ice, so maybe a few centimeters of ice. But we want to make it sure that the ice is thick enough for them to be able to successfully hunt seals. So we use that, and we also use a 10% sea ice concentration threshold, as that was the best fit with the telemetry data. And then we just can look at what the CMIP6 data say in terms of if we just used a sea ice concentration threshold for the ice-free period. This is the observations here with the white, and then we have NASA team and Bootstrap. So we're looking at two different satellite data products, looking at all of Hudson Bay, Southern Hudson Bay, and Western Hudson Bay. And then you can see the distribution of the models. And it shows what I had shown earlier in that in Hudson Bay in particular, the models are overestimating the ice-free period. So if you were to just take those models as is and you go out forward in your projections and try to say, well, how long is the open water period going to be and how will that impact polar bears, you would be quite biased because these models are all biased. If we constrain it with thickness and we say, okay, you need at least 10 centimeters of that ice to be present, then some more models are actually closer to the observations, but you still have this overall bias in the ice-free period. And it was interesting when we looked at that, because if we also look at, for example, the trends in the ice-free period and how that's changing, then it actually doesn't look so bad for the models. So the models are actually capturing the trend overall in the ice-free period. They're a little bit biased low in this case. So the red star is actually the multi-model ensemble mean, but it is still within the range of the observational uncertainty. If we look at the sensitivity, though, with climate change, with global warming, then again, we see that there is an underestimation in general of the ability of the models to capture the sensitivity of how the ice-free period lengthens with global warming. Oh, yeah, sorry, I should have gotten my arrows sooner. But so this leads me into how can we use the CMIP6 models to do bias corrections to try to hopefully trust their future simulations better. And in our paper, we looked at two different ways to do the bias correction. So one is we're picking all the time periods for which the temperature in the CMIP6 models is matching the temperature anomalies that have been observed globally. And we use the best data set for this over the observational period. And so we're just looking at the bias in the ice-free period constrained by this temperature range, which is a more realistic temperature range compared to the observed. And then we use that to adjust all the models with this bias adjustment. So that's just a simple bias adjustment. We also looked at a weighted average following the method that was proposed by Knuti et al. In 2017. So you're basically assigning less weight to models that perform quite poorly to the observations. It also will assign less weight if simulations are duplicating another in an ensemble. And we decided that it would be good in our weighted average to use 8 different variables. So we're really using a combination of whether or not the ice is retreating or advancing, the length of the ice-free period, as well as the regional temperature trends and the global temperature and sensitivity, because we really want to get those relationships so that you're not just weighting models even if they get the answer right for the wrong reasons. So that was sort of our rationale for this. And then we can kind of look at what the evolution would be for Hudson Bay as a function of global warming. So the weighted average is in the red, and the bias adjustment is in blue, and then the satellite observations are in yellow. And we again break it down by southern Hudson Bay and western Hudson Bay. And you can see at the beginning of the time period, we have similarities between the weighted average and the bias adjusted average. But as we go out into the future, the weighted average is going to show a longer ice-free period in both regions compared to the weighted average. So they do start to diverge, and it's about 10 to 15 days longer, depending on how you do the bias adjustment. And this is just a snapshot of what we would expect the ice-free period to look like under 2 degrees of global warming or 4 degrees, but looking at both, sorry, this should be 2 degrees and 4 degrees here on the side, but actually looking at, again, the bias and the weighted adjusted average. So it just gives you a sense of how you would use that data.
One more minute, Julienne.
Okay, so I got to go quickly then. Sorry, so yeah, and this is just kind of a summary plot that we had that was sort of looking at, again, now it's ice retreat and ice advance, and the length of the ice-free period based on either bias adjustment or weighted averages. And basically then we're trying to look at, well, how would this impact the polar bear survivability? And we know that from other studies that it's about 180 ice-free days under which you start having big declines in the adult healthy male polar bear populations. It's a smaller number for females or young adults. So we would expect then at the 2.7 degree target that we're seeing that we would be ice-free between 201 and 215 days in southern Hudson Bay, or 182 to 191 days in western Hudson Bay, depending on your biasing adjustments. But I just wanted to quickly tap on extremes because CMIP6 is great for these long-term sort of estimates, but it doesn't capture extremes, of course. And this year was extreme in Hudson Bay. So in southern Hudson Bay, the ice already broke up in May of 26. And you can sort of see that here of the total Hudson Bay sea ice extent, where it was quite unusual this year compared to any other previous year. And it was the earliest recording opening that we've ever seen within southern Hudson Bay, and it was quite late actually for western Hudson Bay. It wasn't the latest, but it was quite late. So the bears in that region had more time on ice compared to the bears in southern Hudson Bay. And just quickly, what really drove that was we had a reversal of the winds. So we had a switch of the winds now becoming the strongest easterly winds that we have seen in this region. And that's sort of broken down here. We're looking at the zonal wind speed, and you can kind of see the really anomalous zonal winds that we had. We had quite warm temperature anomalies, and we had this huge marine heat wave that persisted all the way through October, with more than 90% of all days experiencing a marine heat wave. And this is why this region has not yet frozen up, even as of January 13th. There's still this open water here in southern Hudson Bay. And because of that, this region is experiencing more than 200 days this year of ice-free conditions, which is similar to that warming level of 2.5 degrees of global warming. Okay, so my last slide. Basically, I just feel like there's such little time to understand the consequences of ice-free summers. I mean, this transition that we're looking at is going to be within the next 20 to 30 years. And there's a lot of key questions that are still remaining. And, you know, especially on the whole entire marine ecosystem, cascading up from the phytoplankton and the ice algae all the way up to larger species like the polar bears and the seals. You know, I think we're covering around this sort of 5 million or below square kilometers every summer. And, you know, the questions are, well, what do we need to get to before we see the next stepwise change? So we are definitely somewhat stabilized at what it looks like at 1.5. And then it's really interesting to think about the role of extreme events in initiating these stepwise changes. So Hudson Bay right now is interesting if it even freezes up entirely this winter or not. What will that then do for the next year? And then finally, I have wonders about how we can use the CMIP6 models best, given that there are these biases and we have to account for them. And that's it. Sorry for running a little over.
Thank you very much, Julienne. Another excellent talk. And I guess you can keep your camera on, and then we can have Morven and Stefan and Letizia also join you for the little bit of panel discussion now. Yes. So, welcome to Letizia, Tedesco, and Stefan Fronzek, who are both senior research scientists at the Finnish Environmental Institute. I don't see Stefan yet, but I think you are here, hopefully. Anyways, I was going to start with a question for you, Letizia. So you work on marine biogeochemistry and polar marine ecosystems, and we've now heard from Morven and Julienne, about the changes in the sea ice and how that also affects a lot of the variables and that characterize the ocean state. We heard about impacts for a sort of large species of animals already, the polar bears. But from your research, what are the potential impacts on marine ecosystems from this kind of changing, more dynamic, less sea ice prone Arctic?
Thank you, Marianne, and thank you, Julienne and Morven, for the wonderful talks to introduce the topic. So the short answer is that it's complicated. And the long answer is that it's complicated. We could talk for hours here. Since we don't have hours, just a few minutes. So perhaps I just want to highlight some key points. First of all, sea ice itself is an ecosystem. So, and the environment that surrounds sea ice, it's another ecosystem. And they are interlinked, but they are also quite different and separate in certain things. If we think about sea ice itself, so in a warmer Arctic, in a more dynamic Arctic, in those regions that are facing thinner ice, thinner snow, more permeable sea ice, we are observing and we might expect an increase in light availability, in habitable space, which might bring on the short term and mid term an increase in primary production. And with an increase in primary production, we also have an increase in bacterial production, eventually in secondary production, which affect all of the system. But there is no doubt that as we are losing sea ice, we actually losing an entire habitat. And that means that we lose biomass and we lose biodiversity. As we're talking about more dynamic Arctic, so different kind of sea ice changes or sea ice type changes, I think Morven mentioned opening, melt ponds. I would like also to mention ridges. In a more dynamic Arctic, there will be more chances for leads opening. And a lead opening, which we have already observed and has been studied in the past, brings earlier production in the season in a kind of different environment where there is, as Morven mentioned, more mixing, more nutrients. At a time of the year, we don't expect primary production. So also different kind of phytoplankton bloom, which can feed a different kind of trophic food web. Talking about melt ponds, also an increase in melt ponds might bring an increase in primary production, especially open melt ponds, which are giving rise to higher biomass. And finally, there's been a very recent work on ridges, on the fact that ridges are on the decline, and also that we are expecting and observing, we have been observed actually as motor surface. Ridges are actually an hotspot of biological production because they create microhabitats within ridges that are very favorable for actually different kind of algal growth. And as these ridges, as we expect more levelized red ridges, this would mean a decrease in production. And this is about the sea ice itself, which cover only a small part, even though we have to remember that sea ice is as big as our tropical forests on our planet. But if we think about the environment surrounding sea ice, I just would like to mention that there are species who are dependent on sea ice for their entire life cycle or some part of their life cycle, which are really key for their survival. And some that we all may know are, for example, ring seals that depend on a thick snow cover for the pupping dance and for the pup survival. And for example, boed whales as well. They are both endemic to the Arctic. Boed whales depends on the phytoplankton bloom at the ice edge in order to feed on zooplankton. And they are both moving north, but of course they will be a certain, they might stay in the north also, and they are staying more and more in the north. And in the long run, what we do expect is a perish of these species because they will not be able to survive. Then there are ice-associated species, means an organism who depend from sea ice for certain part of their life stage, but they can actually survive in a different way. For example, change diet. And example are viruses who can and have been observed to move to land, as well as polar bears. They could actually move to land. And for example, polar Arctic foxes. The problem for these kind of animals is the change of diet. So a less suitable diet, maybe less rich in fatty acid, can in the long run as well bring some changes for their fitness and eventually perish as well. So a lot of changes. And the last thing maybe I want to mention as well is the arrival in the Arctic of new species. We call it new species, but it's quite interesting if you talk with local communities. They have been observing them for a long time. It's just the occurrence of these species has become more noticed. And for example, capulines, Atlantic cods, and for example, Calanospin marquis, they are all moving north. They are taking new niches. And these also mean that some species can live together, but some of them may outcompete or actually are out competing with the local species. So that's another threat, even though some species might survive, but if other arrives and take their space and their habitat and their food, then they will end up not surviving. So
yeah, I can see why we need a separate webinar for
a lot of hours. So biodiversity loss. So well, the changes are enormous. The one that we are looking at already, and the one we expect in the future. Biodiversity loss, possible trophic mismatches because of different phenological timing of biological events, and then migration. And also the last aspect we have to consider is also pollution. The new Arctic, there is more noise, so there is more acoustic problems for several species, including marine mammals and fishes, but also disruption of ecosystem, as well as possibility of chemical pollution, oil spill, and other kind of spill. And yeah, so I'm just touching, the top of the iceberg, but I hope I at least gave you some answer.
I think this gives a good impression of how substantial the changes are, and also a reminder not to forget the very tiny mechanisms or the tiny species, and how they changes in the small scale systems also propagate to the larger species and all the way to the system. Thank you. Stefan, turning to you next. So we've heard so far about the natural system and ecosystems, but these rapid Arctic environmental and climate changes are bound to have broader impacts. You work with climate impacts and risks. What can you say about socioeconomic consequences or impact on humans and society? We hear often about the opportunities from a more ice-free Arctic Ocean, but I'm suspecting that's part of the picture only.
Yes, thank you very much. And thank you, Julienne and Morven, for excellent presentations. And I directly follow up actually on what Letizia was just explaining. And if I extend this to impacts, what does it actually mean for humans? I guess there are the impacts on human livelihoods, and that specifically includes those of indigenous communities. Disappearing sea ice, as we just heard, and what was nicely explained by Letizia, has effects on many species, and including those that are subject to harvesting: polar bears, seals, whales, a lot of the fish stocks that depend on ice cover, and they are directly impacting the livelihoods of communities. And as a result of that, the livelihoods that are connected with hunting and fishing are under threat. So that's maybe the first impact here, impacts on livelihoods. Then we already heard in both presentations a bit of mentioning of shipping, maritime transport, and obviously sea ice retreating sea ice opens up the borders for shipping. Julienne nicely explained the uncertainties related to that, and it very much depends on, well, is it just a couple of days or is it a longer period? But the further we go into the future with increasing warming, there is a larger window of opportunity for marine shipping. And we can actually already see nowadays an increasing number of ships that are in the Arctic, and they affect things like the global trade patterns. There are a lot of the opportunities that are already being realized. The sea ice retreat also improves the access to natural resources in locations in the Arctic Sea and in the central Arctic Ocean, and that has potential benefits for commercial fishing, that there's a tourism increase in the area, and exploitation of non-renewable resources, which brings me to the third point, the resource extraction, which is in the Arctic has an estimated hold of 13% of the world's oil reserves and 30% of the undiscovered gas resources, and as well as substantial deposits of different kinds of metals, which are also needed for the green transition. And all of these are being made more accessible by retreating ice, and we can already see that that there is already increased activity, including recent news from the future President Trump claiming places like Greenland. So that's part of the picture. So these three are maybe the three main impacts on socioeconomic impacts. And the final thing I want to mention here is that these are have the potential, or actually are already cascading impacts that are transmitting effects on other parts of the world. So the Arctic is not unconnected to the rest of the world, but it's obviously through trade that I already explained, but there's also the risk for geopolitical conflict that's rising with the decreasing sea ice. That's for me for the moment, to leave some space for discussion.
Yes. Okay. Thank you. I was checking the chat. I think, Morven, there were a couple of questions for you that I think you already answered. I think people should be able to raise their hand as well if there's a burning question here. In the meantime, maybe I wanted to pick up a little bit on what both Morven and Julienne showed and said, is that the model tools that we use today, they are far from perfect. And I think Julienne in particular, you pointed to the fact that while you might be able to capture the large scale features, when you go into the details of the regions, the seasonality, etc., you start seeing larger biases. And these are also where, when you get into the more kind of actionable information for adaptation, you need to go to these kind of scales. So questions, are how do we move further now? We're kind of entering a period also where we have a lot of focus on the polar research that will continue with a new International Polar Year in a few years. We have a new IPCC cycle just kicking off. So what can the community do within CRiceS and beyond, and then the broader community to address the knowledge gaps, which are the most important ones? And maybe just a quick round and an answer, quick response from each of you. Starting with Julienne, you unmuted.
Yeah.
So.
Oh, yeah. It was really challenging in our paper to figure out, how do we best use these models, right? Because we know that there's biases. And we didn't want to just take the models as they are, because then we're going to be probably even more pessimistic. At least we would have been in Hudson Bay than we are. We're a little bit more conservative. But I don't think there's a really good consensus on how best to try to take the information and take it out into the future, given that there's biases. And I think one of the things I looked at years ago, this was with CMIP 5, is that, just because a model doesn't get it right today, which is an arbitrary calibration period based on the data we have available, it doesn't mean it won't do good in the future. And so, like we just can compare that, just because you get the trend right in this historical time period, you may not get it right in the future, for example. So how do we best use these models? And I think there's still things, of course, we need to improve within the models to get all the physical processes. And, for a region like Hudson Bay, it's really challenging because a lot of the model grid resolutions do not capture even some of the straits that are happening, like Hudson Strait, and some of these narrow passageways that might be influencing how the ice pack is evolving in there. Curiously enough, I didn't show it, but it actually, when I looked at the snow depth on sea ice, because we also looked at the seal populations, but I didn't have time in this talk to do that, the models actually did pretty good with the snow depth distributions, surprisingly, even though the sea ice wasn't as good.
Right.
So they might get one variable
question.
right and not another variable right.
Yeah.
So maybe, I would love to see more workshops about how best to try to figure out how we constrain the future projections so that we could do these sort of biological studies.
Mm-hmm.
Yeah.
Maybe passing the ball back to Stefan again a little bit. You're a user of this kind of model data to assess the impact. How confident do you feel that you can be in your work here?
Yeah, I think it's the approach that Julienne showed is the right thing to go. I think using climate model output from global models directly is, we know that the numbers are not right, they are not reality. So it's just a model world. So it's some sort of bias correction, and bias correction methods have been applied in lots of impact studies for the basic variables, surface temperature, precipitation, but then the more difficult variables like sea ice. It's I like Julienne's approach. Maybe the other approach could then also be looking at regional climate modeling approaches that go down to a finer spatial scale, and where you maybe resolve some of the issues that you are having with the global models. But of course, these are still models, and they are still in model worlds.
We're running close to the end here. One point from Morven, one from Letizia towards the end, very quickly.
Yeah, no, I very much agree with Stefan and Julienne. Like, the devil's in the detail, and there's a lot of work needed, but also already being done when it comes to model development. And we do know that these models are not perfect, and I think that's just important to keep in mind, but that doesn't make them useless. And I think that it's really a question about uncertainty, and something isn't necessarily completely... there's a difference between certainty and uncertainty, and we can, and you need to use the right tool for the right question, and keep that in mind. And like for many of the processes we study, we do know that the models are wrong, and the numbers are very likely wrong, but that doesn't mean that we can use them for a good process understanding, or to see these connections and to build on that, to also figure out how we need to improve the models to understand that better. So it's useful, even though it has a high uncertainty, and that's really where CRiceS comes in, and where we're also identifying which are the most important processes, like, because you can't do it all, and it has, if you change too many things, you also don't know. So this is an ongoing work, but I think it's also very fast going development, where we're learning much more. But we got to keep in mind, even though we're learning a lot about the details, the big picture hasn't changed, and that's also very important to know. Like, many of the big trends and the big variables, like the estimates from very complex models now are quite similar to the very simple models we had already many years ago. So that's both comforting and worrying.
Letizia, 30-second pitch on what the community should do now.
Thank you. I agree with everyone said, and actually I wanted to add what Morven just said about the importance of processes, of including certain processes even into large-scale model and climate model, as we have been doing in CRiceS, because some small-scale processes that are very difficult to implement, they do have very important consequences. And just an example, I've been studying fragile ice in CRiceS, and discovered how important it is for the iron availability to the Southern Ocean ecosystem, and we are working now on having parameterization that can be used also in large scale and climate model. So let's not forget processing for modeling, but also let's not forget how much we need observation from in situ to the larger scale, and improving also satellite products, because we still need observation, especially in certain regions, and especially in the shoulder seasons, which are less sampled.
All right, that kind of concludes our hour. I wish we had more time. There are a lot of topics to pick up on, so let's do that in upcoming events, workshop, conferences. And we have a lot of work still to do. And I think Julienne said she said very importantly, we have little time as well. These changes are happening, and the impacts and consequences are happening now. So let's keep this all going. I just wanted to put up here for you the CRiceS information. Please follow us and then stay up to speed on what we're doing, follow using these channels, and more from us later on. And thank you everyone for joining and for listening, and thank you very much.
Thank you.